We'll go ahead and get started here. I want to thank you all so much for making time in your day to join us for our session today. We're going to take a look at Rust at full speed, harnessing concurrency with confidence. Before we get started into the actual content for today's session, a couple of things about us. One of the goals here at Training for Programmers is to deliver training that is human-centered, AI-empowered. So that means we do live sessions where you have an actual human being talking to you, answering questions. We're also AI-empowered. We make use of tools like GitHub Copilot and other generative AI tools to do programming, to learn how to do programming, so on and so forth. And we feature those tools in the different classes and stuff that we teach. Our goal here for these sessions is to deliver the same high quality, big corporation programming training, but to everyone. Some of the classes we offer are free, like this one. Other classes that we will be offering will be paid classes. They'll be offered in a variety of price ranges, but the goal here is to take training that is typically limited to corporations and make it available to everybody in the world. We want to deliver training that can be taken by anyone that has a web browser and an internet connection. You don't have to have a super powerful computer. You don't have to have development software set up ahead of time. You could go to your local library or an internet cafe and be able to participate in our courses. We want to focus on in-demand languages. That's why we're focusing in on Rust for these initial trainings that we're doing, and frameworks so that you can take what you learn here and get yourself a high-paying job. Another thing we want to do with these trainings is allow people to learn where they live and then also to get jobs where they live. A lot of times people have to travel around the world to find good education or to find good job opportunities. With the power of the internet and the software that we have available today, that's not necessary unless, of course, you want to travel around the world. So we want to deliver these trainings to where people are so they can benefit themselves, their families, and their local communities. And then finally, as I mentioned, leveraging AI tooling to learn how to do things and develop our programming skills. Now, I typically have this slide at the end of the presentation, but at the end, we're usually trying to get in those last couple of demos, so no one ever sees this slide. So I thought I would put this up here at the front before we actually get into our coding. The first thing I'd like to do is I'm going to put into the chat here real quick a link to our YouTube channel. A lot of the recordings and videos and other things that we produce ultimately end up on that channel in one form or another. If you'd like to visit that, like the video, subscribe, offer comments, we would definitely appreciate it. Also, our primary way of marketing ourselves to people to let them know about these trainings is on LinkedIn. If you'd like to visit our company page and follow us, that's one of the best ways to stay aware of future trainings that we're going to be offering. And we have kind of a little temporary website up at the moment. We have some bigger plans for that coming down the road. But technically, if you go to the site, you can see the trainings and stuff listed with links to register and everything else. The last thing I'll mention, then we're going to jump right into our content here, is we have a Discord group where we're trying to build a community of programmers around the world who want to collaborate, discuss code, things like that. If you like Discord and you want to participate, I encourage you to join. At some point, I will be offering things like office hours and other sessions like that within the Discord platform. So if you have an interest in being a part of that, there's the link to join us on Discord as well. Okay. The currently scheduled upcoming sessions, although there will probably be a few more before we even get to July, but the ones that we have scheduled at the moment is in about a week and a half, we're going to talk about enums, structs, and traits. They're kind of the essential building blocks of Rust programming. So the previous webinar we did a week ago, we talked about memory safe programming. Today, we're talking about concurrency. The next one, we're going to be tackling these topics. And then the build web apps with Rust and Leptos. We had scheduled that class a few weeks ago, but I had to cancel due to scheduling conflicts, and we actually were charging for the class. But what I decided to do, because of popular demand, was to A, offer it again, B, make it free. And that's when we're going to be offering it right there on July 3rd. What's interesting is I've had a lot of people sign up for this class. I had no idea the demand for Leptos would be so high. So if you have an interest in learning how to build web apps with Rust and Leptos, Leptos is a full stack web framework that also makes use of WebAssembly on the client side. If you have an interest in that, I would encourage you to check that out. You'll see various promotional links and emails and stuff coming out that have links to register for it. When you see that, make sure you sign up for it. Last thing I'll say, like I said, this is the slide nobody ever sees. First of all, thank you all so much for registering for this and attending. Second, after the session is over, you have access to all the source code. You'll be getting access to the recording. Go back and review what we talk about. If you have any questions about anything, just go to Discord, ask the questions there, and I'll be answering them for anybody who has them. Within 72 hours of the event being over, I will send you the recording, and I will send you a badge so that you can put that on your LinkedIn profile if you want to. Only people who attend in person get the badge. So that's my way of saying thank you for making the effort to actually be here while we're doing the live session. Follow us on LinkedIn and Eventbrite to stay up to date. Also, I'm going to be giving out an end of class survey about halfway through. And if you don't mind taking that and filling that out, the feedback that you offer on there, I really do read and factor into future topics and things that we're going to be talking about. With all of that said, let's get into talking about Rust. For those of you who are not familiar with Rust, let me give you a quick overview. Rust is a fast, memory-safe, and concurrent systems programming language. We're going to be specifically focusing in on the concurrent part of it today. You could kind of think of Rust as an alternative to like C or C++, but I'll be honest with you, I use Rust for a lot of things when where I might have ordinarily used Python. But once you kind of learn how Rust works and it starts to make sense, a lot of things are just as easy to code in Rust as they would be in Python once you know Rust. Now, if you don't know Rust, it's got a steep learning curve. But once you know it, there's a lot of things you can do with it that you wouldn't ordinarily think of Rust for. And one of the things that I love about it, it is very, very fast, much faster than Python. Also, with all of the memory safe features and things like that, I have an increased confidence that what I'm coding is actually behaving the way it's supposed to. Rust has many other features. It has some novel ways of handling nulls through the optional type or through the option type, handling errors with result. It also has things like zero cost abstraction so that you can have higher level features with no performance penalties. And like I said, you can use it for programming operating systems. You can use it for doing IoT development. You can use it for web servers, but you can also use it to write task automation scripts. It works really, really well for that. So hopefully as we go through this, you'll be able to see some possibilities of what you can use Rust for. And that'd be great for you to start learning how to do that so you can make use of it in your stuff. Now, as we go through, if you have questions, feel free to put the questions inside the chat or the Q&A. I kind of prefer the Q&A box on Zoom here for the questions, but if you put them in the chat, that's fine too. I'll do my best to kind of scroll back through. But the Q&A box is really the best place to put them. In terms of Docker being made with Rust, I want to say Docker is mostly written in Go. I could be wrong about that, though. I haven't specifically investigated what Docker was implemented in. I use Docker all the time, but I want to say, if I'm going back in my memory here, I want to say it's more Go programming than really Rust programming, but I could be wrong about that. Okay, so with that said, let's go ahead and start doing some programming in Rust. Now, the way this is going to work is I have a public GitHub site that I'm going to share with all of you. I'm going to drop that into the chat right there. Okay. So in the chat there is this public GitHub site. This GitHub site is set up so that you can launch a code space if you want to. If you are logged into GitHub and you have code space hours, free ones still available, or you want to pay for them, what you can do is come up to here and fork the repository. Then once you fork the repository, you can come under code spaces and there will be a big green button that says create a code space. Make sure you create the code space on your fork. That way you can commit any code changes back. If you create a code space off of the public, off of this specific repository, you won't be able to commit any changes. So if you'd like to kind of code along with me and run the code, click on fork, then create your code space. Once you do that, you'll have something that looks like this that'll pop up for you. We'll give it a second here to reload this. It timed out on me. And essentially what it is it's VS Code in the web browser. And it all runs inside of a Docker container. And you can run the Rust programs directly here in the web browser with zero setup. This is what I was talking about before when I said you could be in a public library and be able to run this code. We do that through the use of code spaces. Anyways, with that said, let's go ahead and dive into our code samples. You'll notice here that I've got 16 of these. I don't know that we'll get through all of them before the end of our time together. Or if we do get through all of them, I'll probably be rushing through the last few. If that's the case, remember, you can always come back here and look at the code and review it on your own time. And if you've got a question on something we didn't have time to really discuss, you can go over to the Discord group and ask your questions over there, and I'll be more than happy to answer. Okay, so let's walk through this and let's see how long it'll take us to get through all 16 of these. So the first thing I like to talk about when I teach concurrent programming is I like to talk a little bit first actually about what is concurrent programming. So in the world of multiple cores, even multiple CPUs, and writing software, the question often comes up, is there a way that I can leverage the capabilities of my CPU, especially if I'm having to access I/O resources? Is there a way to leverage the capabilities of my CPU to get the max amount of performance that I can out of my program? Well, the answer to that question is a little bit tricky. If you have a program where, let's say, you've got 5 steps, and step 2 depends on step 1, and step 3 depends on step 2, concurrency is not going to help you out at all because you have to do things in a certain order. But if you have a situation where, let's say, in step 2, you have 5 independent things that you can do, and you could then run those 5 independent things either concurrently or in parallel to make better use of your processing power. As long as they're independent, you can do that on modern CPUs with modern programming languages quite easily. And that's where the power of concurrency and parallelism come in, is when we have things that are truly independent and we can kind of run them all at the same time and be able to then get their results back and then make use of those results. In the world of concurrency and parallelism, we have a couple of different ways of describing this. When people talk about parallelism, they're really talking about literally doing 2 things at exactly the same time. To do that, you need multiple cores or multiple CPUs. When we talk about concurrency, we're generally talking about making progress on multiple things at the same time. So I'm not necessarily doing them at the exact same time, but I'm making progress on one and then making progress on something else, and then going back to the first one and continuing to make more progress. A lot of times when you're accessing things like I/O resources, the slow part of your program is calling that REST API or reading data off of disk. Well, while you're waiting for that response from the REST API, in the concurrent programming model, you could have another independent task working on something while you're waiting on data from the first task. That's the idea here. Well, depending upon the programming language that you're using and how it goes about implementing things like concurrency and parallelism, you have different options available to you. Here in Rust, with what we're going to be taking a look at here today, a couple of the options we have are multi-threading and asynchronous programming. With multi-threading, we basically have our one process, but within that one process, we have multiple lines of execution, and they all share memory. You could start to imagine some of the potential problems with that, right? Having these different lines of execution, sharing memory, and the different problems we could have with them trying to read and modify memory at the same time. The cool thing is about Rust, as part of its memory-safe programming, it's going to help protect us against making mistakes in that area. And we'll be exploring that in the demos we're going to be looking at here today. Rust also supports thread-based parallelism. So what that means is that the threads themselves can actually run on the different cores, giving us that parallelism benefit. I highlight that because languages like Python, while they support multi-threaded applications, they don't do thread-based parallelism because of limitations by things like the GIL. So just because a programming language supports multi-threading doesn't mean it can do thread-based parallelism, but Rust can do thread-based parallelism. The other concept we're going to talk about is asynchronous programming. The idea in asynchronous programming is I can get a lot of the benefits of multi-threaded programming, but with a simpler memory and execution model. Now, the interesting thing about Rust is that its asynchronous programming is actually a little more complicated than the other async models you'll see used in other languages. We'll talk more about that when we get to the second half of our coding demo, and I talk about asynchronous programming. But for now, what I want to do is I want to start off here with the basics. And the basics is, how do I even tell a thread to go to sleep? The reason why this is important is that thread sleep is a great way for us to be able to test our concurrent code. It's also a great way to nudge the operating system to switch threads. Now, of course, if we're running threads across different cores, that's not as big of a deal. But if we're running multiple threads on the same core and we want to see it actually switch threads, thread.sleep is a good way to do that. So let's take a quick look here at this code, and I'll show you how to run these examples. So the way I have this set up is I've got 16 individual projects, and then I've got kind of one big wrapper cargo toml file here at the top. Let's say I want to come in here and run this thread sleep code. The way I'm going to do that is I'm going to change into projects, and then I'm going to go into thread sleep. And then what's going to happen is I'm going to say cargo run. And when I run this code, you'll see we have hello output, then a sleep, and then goodbye. So to simply make use of thread sleep here, all I had to do was bring the module into scope. Then I can call the sleep function. And then we have this duration. The duration has a number of different functions here where you can specify the different units of time that you want to set that duration for. And so here I have it in seconds, but I could have also done it in milliseconds, so on and so forth. The reason I'm taking the time to tell you this is A, you'll be seeing a lot of it in our code. And when you go to do your own concurrent programming, a great way to test to see if it works is putting those random sleep statements throughout your concurrent code. With that said, let's go ahead and actually get started working with some actual threads here. So we have our main function, and we're going to use the thread spawn function to actually create a new thread. When you create a thread, this new line of execution is running in the same process. We are not creating separate processes on the operating system. The thread is running in the same process. It is also sharing memory with the other threads in that process. Now, in order for the thread to run, we have to give it some code to execute. We're going to set that code up here through the use of a closure. A closure is nothing more than just a function. If you have experience with a language like JavaScript, you could think of the closure as an arrow function. In a language like Python, you could think of it as like a lambda function. Now, these closure functions, unlike lambda functions in Python, actually can have code bodies, which is what you see here, just like arrow functions in JavaScript. Anyways, the pipe symbols that you see here, this is basically saying this is the function parameters, of which we don't have any for this function. And then, of course, we've got the function body here. Now, inside of our closure here, we have a loop. And essentially, we're just going to print something out, and then we're going to have it sleep for a moment, and then loop around again. Down here, we're going to do a similar looping mechanism. But what's going to happen here is we're going to be running this code on the main thread. One of the things you have to be careful about with multi-threaded coding is realizing where the code is actually executing. This is where a lot of people get stuck when they're looking at code like this kind of all in one big method, but they don't realize that because we're doing the multi-threading, this code here is running on one thread, this code here is running on another, even though the code itself is co-located within the same main method. Now, down here, we have a function called join that we're going to call on the thread handle. Join basically means our main thread is going to block and wait for this thread to finish before continuing on. It's going to block and wait. So let's run this code and let's see what it actually looks like when it runs. So I'm going to go to the O2 folder. I'm going to type cargo run. We'll let this compile. Now take a look at the output here. Do you see how we're in main thread 1, spawned thread 1, main thread 2, spawned thread 2? Well, actually, we just have the two threads, main thread and spawn thread, but you can see the incrementing of the counter from the I here. Anyways, you can see we are jumping back and forth between the threads. We don't really have any control over that. The operating system is just switching between threads as the program is executing. And so you can see the output here. Now, in this code, we are not sharing any memory between the threads. So you don't see any variables declared out here in main, and then I'm referencing those variables inside of here. This code has no memory issues because no actual memory is being shared. So when we talk about memory being shared between threads, what that literally means is I have a variable in main, and then I'm referencing that variable inside this closure. In the next demo we're going to see an example of what that looks like. But that act of putting a variable out here and referencing it in here, that's where we start to get into the shared memory issues. But as long as this closure doesn't access some variable on the outside, we really have no threading issues in terms of dealing with memory. The last thing I'd like to mention before we jump to the next example is I want you to take a look at this handle.join. This join is basically going to consume the handle. As you all know, when you work in Rust, you have to think about the ideas of ownership and borrowing and moving ownership basically from one call stack or from one stack frame to another stack frame. When we call the join method here, the handle that we have created is actually going to be moved into the join, and we're going to lose access to that handle out here in the main function. So if I were to come down here and say print line, you will see I get a red squiggly and it says a borrow of a moved value. I can't borrow this anymore because we have moved it into join. If you had joined the session a week ago where we talked about memory safe programming, in some of those examples I showed where I created an instance of a struct, passed that into a function which caused it to move. And then if I tried to access that same variable later on, I couldn't access it anymore because it had been moved. That's the same concept happening here. As we go through the demos, this idea of the handle being moved, being consumed by the join, is going to impact how we write our code at times to call join and wait for these operations to complete. But we'll take a look at that here in a little bit. For right now, I'm going to comment this code back out. So now that we see the basics of how to fire up a thread, let's take a look here at how we can share data between threads. Now, this is where things start to get a little bit more complicated. If you've never really learned about memory safe programming in Rust, this is definitely going to be a little bit challenging. However, don't place the burden on yourself to have to understand all of this perfectly the first time. I promise you, the first time I ever used Rust, even though I had done lots of concurrent programming and had been programming in lots of different garbage collected and non-garbage collected languages over the years, it took me a little bit of time for this idea of ownership and borrowing and moving and how to share data between these threads. It took me a little bit of time to understand it and really let it sink in. So if you're super new to this, just be patient with yourself as we walk through this next piece. So in our main method here, I have a counter variable. Ignore the data type here for a moment. Just focus on the fact that it's a counter variable and it's a number. Inside of my thread that I'm going to create here, I want to increment that counter variable. So I have a counter. I'm going to run a bunch of threads. In each thread, I want to increment the counter. Down here at the end, I want to print the final counter value. If I write all of the code correctly, then my counter should be equal to the number of threads that I've created. So if I have a counter of 0, I launch 10 threads, all 10 threads incremented by 1, the final value of counter should be 10. That's pretty easy to follow. But the actual mechanics of how you implement this in a Rust program, that's where things start to get a little bit more difficult. So first of all, I can't simply create a counter of, let's say, I32, and then just directly reference the counter inside of here. That's just not going to work. You could do something like that in Python, and it would work, but you're not going to do something like that in Rust. The memory safety is going to be much stricter than that. So what we're going to have to do here is this. First, there's our actual 0 that we're initializing counter to. We're going to wrap this into a mutex. A mutex is a mutual exclusion lock. What it basically means is that one executing piece of code can have access to this value at a time. Okay, now it could be reading the value, it could be writing the value, but only one thread can have access at a time. Now, when I first learned about concurrent and multi-threaded programming, I thought to myself, well, of course, only one thread is going to be running this line of code at a time. What's the big deal? Here's the thing to remember about multi-threaded programming. Rust is a lower level language, but it is still a very high level language relative to assembly, relative to the opcodes running on the processor. This might be one little line of code in Rust, but it could be 30 lines of code in assembly. When the operating system switches between threads, It's not switching between threads based upon the lines of code in our Rust program or Python program or Java program. It's switching between threads at the opcode level. So an opcode finishes on one thread, which could be like half of this operation, and then it switches to another thread to run. So the problem with the shared memory is our program could be halfway through executing this single line statement, switch to another thread running this same code, and now you start to see where the conflict comes in. So to help prevent this from happening, we have a mutex that we're going to be passing through, or we're going to be tracking the data with and controlling access to it. But here's our problem. The mutex isn't enough. You see, we need the ability to actually modify that mutex value. But our problem is that in Rust, we can only have that one mutable reference at a time. Well, we're going to have 10 threads running that are all going to be wanting to change this value. We can't just have 10 mutable references on the mutex itself. So what we're going to do is we're going to wrap this in a data type called an atomic reference counter. This reference counter is going to give us a safe way to access that mutex and modify it across many threads. So up here in the main function, I'm declaring my counter variable. Then down here, as I go to create each thread, I make a clone of the atomic reference counter. I then move, so we're moving ownership of the clone into the closure. And then inside the closure, I can use the functionality of the mutex to gain a lock on that data and then increment it. So this ensures that only one thread at a time has the ability to access this data. Now, of course, using a mutex like this basically turns our program in terms of execution into a single-threaded program, because all of the threads are going to have to wait to get a lock on this value before they can modify it. You'll want to think about that when writing your software. If all of your independent threads are all dependent upon updating one value, if they're not doing other independent things, then you're not really gaining anything with concurrency. In this case here, we're not so much worried about are we doing other independent things. We just want to see how the counter is going to be able to increment. So down here now, we have a loop where we're basically going to wait for all of those threads to join. And then once they all join, we can print out the result. We don't want to print out the result, but before all the threads finish, we may not have the latest counter value once they're all done. So now if I come into here and I run this, you can see the threads, and I have the sleeping for a random number. At least it should be random. Anyways, you can see the result there is 10. Okay, so it actually did the adding and stuff correctly. Now, what would happen if I didn't use the atomic reference counter, or I didn't do the unwrap? You'll actually get compile errors from Rust. I'll show you an example a little bit later on. We'll use like a reference counter instead of an atomic reference counter, and you'll see the program won't even compile. Okay, and by the way, that lack of compiling when you use these concurrency types, when you use these memory, or you use the different memory types incorrectly, that's one of the big benefits of working with Rust and doing this concurrency with confidence. All right, let's take a look here at another lock. This one is similar to the last example, except here's the difference. With the mutex, only one thread can have access to the mutex at a time, whether it's reading or writing. What the read-write lock does is it actually allows multiple threads to be readers, or one thread can be a writer. The read-write lock is actually very similar to how references and mutable references work in Rust. As you know, you can have multiple references which are read-only, or you can have one mutable reference to that variable and you can modify it. That's the idea behind the RW lock, but instead of applying it just as a memory safe thing in the programming language, this is actually a locking mechanism that we're using across these different threads. Once again, we're going to wrap it inside the arc. Now, let's take a look here at how this is going to work. Up here, I've got 5 threads that are going to be created that are going to read the value. I have one thread that's going to write to the value. If this code works as intended, I should be able to have multiple threads do the first read without having completed the second read yet. So thread 1 can do a first read, thread 2 can do a first read, right? And then eventually they'll all do the second read. But thread 2 didn't have to wait for the first thread to finish both reads before being able to read it. However, when this thread is actually getting a lock to actually write to the data value, then none of these threads should be able to read it at all. So let's come into here and let's run this code. And I'm going to go to the 4th folder there, or attempt to. Let's see. Or 04. There we go. And we'll say cargo run. So you'll notice here, thread 1, 2, 4, 3 were able to start reading. Then, of course, they did their second read. And then once they finished their second read, then the right one was here able to run. And then I guess we had this other thread that was hanging out there, and now it's doing its read once it was able to get a hold of that lock. So you can see we don't have any situations where I have a first and a second on either side of the writing. In order for the writing to work, all of these locks had to be given up so we could then write. And then once the writing was done, anybody who wanted to read could start reading again, which could have been multiple threads if we wanted. Now, I want to highlight something here real quick about these locks that I did not mention in the previous demo, but it also applies to the previous. You'll notice here that when I get the lock, I never unlock it, right? So in some programming languages, you get the lock and then you explicitly have to release it. Other languages, let's say like Python, will use things like a with block. It sets up a context, and when you enter the with block, you have the lock. And when you exit the with block, it releases the lock. That's kind of what Rust is doing here. I get the lock, and it will automatically drop the lock once I leave the code block. So once I leave the scope that I'm in, it'll actually automatically drop, and that will release the lock, allowing other parts of the program to acquire that lock if they want to. Okay, let's move on to our next demo. Don't forget, you're welcome to ask questions in the chat as well as the Q&A as we go along. Let's talk here a little bit about atomic types. One of the things you might feel a little bit overwhelmed with when you work with concurrent programming, and this is not just true of Rust, it's true of all the other languages too, is all the different strategies and data types that you can work with to deal with these shared memory issues, okay? So here is another example of a type called an atomic type. Languages like Java, for example, have atomic types, like atomic integer that you can work with. And the idea is the atomic type kind of has all the locking and stuff all kind of built into it. If you want to think about it like this, with the read, write, and mutex lock, I had to actually get a lock. I had to do things like this to dereference the interior value to then be able to change it, things like that. This approach here with the atomic types handles a lot of those details for you. So if you have an atomic type that aligns with whatever data you're storing, this can be a more convenient way to kind of work with things and be a little bit less in the weeds on having to implement all the details. Let's take a look at how it works. So with the atomic type, I'm going to use a function here to actually access the data, increment it. In this case, we're going to be giving it an instruction on how that data is going to be changing. So you're a little bit more limited in what you can do, but it's actually much easier to work with because all I have to say is fetch add, and it will fetch it and then add one to it. Same thing down here for decrementing the counter as well, okay? So I have this function here called handle request that receives an arc of our atomic U size, which is the active connections here. And so what's going to happen here is we're going to take that atomic U size and wrap it in the arc. Now, while the atomic does make it easier to get the lock and modify the value, we're still using the arc to actually share this across the different threads, okay? So here we have our thread to print the active number of connections. So we're going to launch a thread that's simply just going to read this value and print it out every 500 milliseconds. Down here, we have another loop where we're going to fire off a bunch of threads that are going to act like incoming connections, like maybe into a web server or something like that. Each time one of these connections comes in, we're going to be incrementing the count, going to sleep for a little bit, decrementing the count. And while these other threads are spawning and running and waiting and terminating, this thread's going to continue running behind the scenes every 500 milliseconds and showing us what that active count is. So if we come down here and we run this code and we say cargo run, you'll see 0 connections, new connection up to 2, those 2 close, another connection comes in. You can see using this atomic U size, we're actually able to easily update and read this value without having to do all of that manual unlocking and stuff like that, and then dropping and everything else. Anyways, it's completed. So if you're working with a data type where there's this predefined atomic that you can work with, that can be really, really helpful. Now, if I come down into here, we have our 4 handle in handles, but you'll notice here, this code's a little different. So if I came back over to here and open that to the side, when I did my looping down here, you'll see that I just iterated over handles and I said handle join unwrap. But down here, I'm going to get a little bit more fancy. I'm going to say handles into iter and then skip 1. Well, the reason why I'm saying the skip 1 is I want to skip the handle that was pushed on by the monitoring thread. So that's what the skip 1 is for. The problem, though, is in order to use the skip 1 function, I have to use that on an iterator. Even though I can iterate over handles here, it's not actually a full-blown iterator in the sense of using the iter function. So if I want access to skip, I'm going to have to use the iter function. But here's the problem. If I use the regular iter function, which just deals with references, see how that changed to the ampersand there for the join handle? I now get the red squiggle. Why? Because as we talked about earlier, the join method consumes the handle. So if I'm only getting a reference here, I can't do the consuming. This is one of these examples that would be really, really frustrating to somebody who's never worked with Rust before. You look at this and you're like, okay, handles, iter, skip, I get it. I'm going to iterate over the handles. But now when I call handle join, it says cannot move out of handle, which is behind a shared reference. Many people have gotten this error message before and like threw up their hands in frustration. Why is this not working? Because this would never be an issue in any other programming language. Well, the reason why this is an issue is because when I said .iter, instead of getting the handle such that I could consume it with the join, I now am just getting a reference. And that's where this method comes in. Within toIter, it's going to give me an iterable that allows me to consume the elements that are being generated by the iterator. In this case, that are in the vector. So by saying in toIter, notice the ampersand is gone, and now I can say handle.join. Here's the thing, though. Can I write this line of code? The answer is no. You can see the red squiggle right there. I can't write that code because once I consume all of those handles, that vector is no longer available to me anymore. So once again, another example of the memory safety stuff. So over here, we didn't have to worry about that because we didn't have to call skip, which means I didn't have to call .iter. But because I need to call skip, it results in this extra level of memory checking, and some might even call frustration in trying to write the code. Okay. Let's take a look here at our next one. Atomic USI is an example of a zero-cost abstraction. You know, that's a good question. Let me think about that for a moment. I'm going to say yes. That would be an example of a zero-cost abstraction. However, that is actually something that I think is worth me taking the time to actually look that up. So I'll say yes for the moment, but I'm going to double check myself on that. And I'll put the answer over in the Discord group. So if you want to check out the Discord group for the answer, I'll post that up in the next 72 hours or so when I send out the other emails and stuff. But that's a great question. Thank you so much for asking. Okay. Let's jump into our thread communication channels. So one of the cool things that we can do with threads in Python is we can communicate between them. When I think of this like in relation to a language like Python, I kind of think of thread queues. You can use thread queues to communicate between the different threads. Same kind of thing here in Python, not in Python, in Rust, we can use channels. So let's take a quick look at what this looks like. So here, we're going to create a channel. It returns back a tuple to us. We have a transmitter and a receiver. In this case here, we're going to have a thread that's going to transmit strings. Down here on the main thread, we're going to use the receiver to receive those strings. Okay. So it's really pretty straightforward. Just create the transmitter and the receiver, call transmitter with whatever data you want, and then be here to receive the messages that are being sent. So we'll come into here, and I'm going to go up a folder. We'll say cargo run. And you can see we're sending messages, and now we are receiving them. Okay. All right. Let that finish here real quick. Awesome. Communication channels, by the way, can be useful if you have, sometimes when we think of threads, we think of doing truly independent operations. But sometimes you could almost think of threads as like an assembly line. So one thread does the initial processing, the next thread does maybe step 2 of the processing, step 3. Using something like a communication channel is one way of communicating information between those threads so that, let's say, the thread for step 2 knows that the work for step 1 has been accomplished. Let's talk a little bit here about a condition variable. You'll see that a lot of the stuff that we're kind of exploring here is shared memory. How do we notify one thread about something that happened in another thread, that kind of thing. It's all about this communication and shared memory. So the conditional variable essentially allows me to have a variable that waits for a certain value within a thread before that thread continues processing. So for example, here, we're going to create a thread. And inside of this thread, we have this conditional variable that we're going to wait until started is true before we continue processing. Down here, we have, in our main thread, we have some code that's going to notify that conditional variable once it should be notified and it can continue processing. So where did this conditional variable come from? Well, up here at the top, we created this mutex, which is a true-false value, and this conditional variable here. And we've wrapped them up together as a tuple within an arc. Down here, we'll create our clone, and then we're going to move that into here. Now, we're going to get into a little bit of symbol stuff here. We're going to get basically a reference to the pair clone, and we're going to access the data inside of it, and we're going to get our lock and our conditional variable. The started, this lock variable here, we're going to get access to it, and then we're going to read the data from it. Now, this conditional variable is blocking, which means we're only going to continue processing this once this is going to be set to true. Here's the thing, though. Conditional variables or threads using conditional variables can have what are called spurious wake-ups. It's when we've told a thread to wait to stop processing until some condition is met, but for whatever reason, it comes back to life anyways. Because that's possible, that's why we have the while loop here. Essentially, we're going to wait, and if for whatever reason this thing comes back to life, if started is still equal to false, then we're going to stay in the loop. If started is now equal to true, then we can continue processing. So if you're wondering why that while loop is there, it's to protect against spurious wake-ups. Now, down here when this runs, we'll simply notify once our Boolean flag is set to true, and all is good. Keep in mind that this started and the cvar are both coming from, ultimately, our original pair here at the top wrapped in the arc. So this thread and this thread are both accessing the same underlying lock and cvar variables here in our code. Okay, let's come here into scoped threads. So this is actually going to use a package here, or a crate, I'm sorry, called Crossbeam. As you've seen in the earlier examples, when I fired off multiple threads, I always had to have that loop at the bottom that would basically join all the threads, once they all finish so we could continue processing. Using the Crossbeam package here, we have an example of what we would call a thread scope. In this code, I'm creating multiple threads, but you'll notice there's no vector of the handles. There's no iterating over the handles. There's no joining or anything. That's because the thread scope here handles all of those details for us. So if you're looking to create like a scoped thread environment where you don't have to like wait for all of those things to join and everything else, and you want your library code there to handle that for you, you can make use of the Crossbeam crate. Okay, let's take a look at a little bit of a practical example. This isn't like the most sophisticated thing ever, but it's a good example of let's have Rust do some independent processing and leverage these threads. So what I have here is I've got some Apple quality data. So in the data folder here, there's a CSV file. I downloaded this data from Kaggle. So if you go to the README here, I've got a link here that shows you where I got the data from, so on and so forth. And in this code, what we're going to be doing is I'm going to read the file into memory. I'm going to create an arc of all of that apple quality data. Then what I want to do is I want to basically get all of the records for the good apples and all of the records for the bad apples. So if you come under data here and look at this, there's a bunch of numbers for different qualities. And at the very end, each apple is marked as good or bad. You could imagine using this data set for some type of machine learning exercise where you're going to train a model off the numbers to classify the good and the bad. We're not doing that here. All we're going to do is come into here and we're going to load the data up. Then we're going to have one thread go off and calculate a bunch of numbers for the good apples, repeat that same process for the bad apples, okay? Now, if this was Python code, there would be no point to writing this code the way that we have. This is all CPU intensive code. Once we're done reading data from the file, everything is just in the CPU. Python, even though it supports multiple threads because of its GIL issues, it wouldn't benefit from creating extra threads to do the processing. But languages like Rust, C++, and other languages, when they do multi-threading, they can benefit from thread-based parallelization. So when I create these two threads, it's not a guarantee, but they could run on different cores, meaning I could be calculating my apple data for the good apples at the exact same time I am calculating my data for the bad apples. Okay, so if we take a look here, I'm going to basically get all of the good apples out, and then I have a summarize function here. I'm going to come into here and get all of the bad apple data out, and then I'm going to have a summarize function here. That summarize function, not overly critical to what we're doing, but if you want to see what it looks like, it's over here in the apple quality file, and you can see where we are going to go through and calculate these values. Now, down here, we're going to basically wait for our threads to complete. In this case here, we're going to be returning the result of summarize apples, and we're going to be able to access that data down here like this. And then we're going to be able to display a summary table that compares the good and the bad apples together. So we'll come into here and we're going to go under, let's see, it's going to be folder 9. And we'll say cargo run. All right, let's take a look here. So here's our calculations for our good and our bad apples. So you can see here, the good apples seem to have, in some cases, very opposite numbers to what you see here for the bad apples. But you could go through and look at this, and if you wanted to do machine learning, I guess, to try to figure out good and bad apples, you could. But in this case here, we're just basically calculating these averages up. With that said, let's go ahead and move to our next example, which is going to be an example that we actually looked at in the previous webinar, where we basically did a GitHub user check calling out to the GitHub website and validating whether or not a user was an actual user. So I'm going to go into here and I'm going to use this to also talk about not using the appropriate data type for sharing memory between threads. So we'll go into here and I'm going to open up the main file. So you can see here, I have a method called fetch user. It just uses the request library, but you'll notice I'm using the blocking version. I'm not using the async version. Down here in demo 16, after we learn about asynchronous processing, we'll use the async version, but we're using the blocking version. If you're going to be firing up multiple threads, the blocking version is more appropriate than using the async, unless each thread's going to be asynchronous. But but we're going to use the blocking version here. Now, if we come into here, you'll see we're going to call our client. We're going to just call GitHub with some username and take a look at the status of the result. This is actually an interesting example of using enums that can also include data associated with whatever variant is selected. We'll talk more about these kinds of topics in the next webinar coming up. Anyways, I've got a list of some GitHub usernames here. And all that's really going to happen is we're going to basically call out to GitHub. We're going to fire off a thread for each request. We're going to take a look at the result that comes back, and we're going to increment the counter accordingly. Down here at the bottom, I'm going to display the total number of GitHub users found. So each one that's found, we increment the counter. Very simple, very similar to the earlier counter example that we did. So if I come in and run this code and say cargo run, you'll see it comes back and says, after it's done compiling. This is the big thing that everybody kind of complains about with Rust, is because of all the checking that it's doing as part of doing the compiling, it takes a little longer to compile than other languages do. We're almost there. Okay, so you'll take a look here, and only 3 of the accounts are legit, but you can see that it did count that number for us. Now, let's say I'm new to concurrent programming. Maybe I'm new to Rust, and I want to track this value. I understand that I need to basically create this reference counter, but I don't know about the arc type. Let's say I accidentally pulled this type in. Then I came down here and accidentally created this. And then I came down to here and changed that to be an R, like that. You see how this whole thing lights up? Standard RC cannot be sent between threads safely. When I chose the wrong data type, the whole thing broke. It won't even compile. It's not even a matter of running and getting an error. It won't compile. So this is part of that idea of harnessing this power of concurrency with Rust, but doing it with confidence. Because if we make a mistake like this, in other languages, your code might actually work on your machine, but then later on have problems, other runtime problems in production or somebody else's computer, what have you. Rust won't even let the code compile. And this is one of the reasons why I like using Rust. I feel more confident in my code when I have a compiler that's paying extra close attention. It's kind of like those of you who have done JavaScript coding and you move over to TypeScript and you start to realize, wow, it's nice to have this static compilation of my TypeScript code, right? And then coming to Rust, you're not only getting the static compilation, but you're getting all the memory checking and everything else, the memory safe checking and all that good stuff. And that also extends to working with concurrency as well. Let me undo those changes. That way we get rid of all the red. Okay. What we're going to do now is we're going to shift gears over to asynchronous programming. These examples are a little bit simpler and less involved. We shouldn't have any problems getting through them here in the next 15 or 20 minutes. So, asynchronous programming is the alternative to multi-threaded programming. In most other languages, when you choose to go the asynchronous route, it involves a little more overhead than what pure multi-threading does. But in other languages, when you go the asynchronous route, you don't ever have to deal with shared memory. So for example, if you look at a Python program that does multi-threading versus a Python program that does asynchronous stuff, you'll notice in the multi-threaded code, you often have a bunch of locks and stuff managing shared memory. But in the asynchronous version, none of that exists. In languages like JavaScript, it's asynchronous by design. So there's no concept of memory locking because everything is asynchronous. Here in Rust, unfortunately, it's not quite that simple. We're still going to have to deal with some of these shared memory locking issues because of the way Rust is validating and compiling and checking everything. However, we can still leverage asynchronous programming and still get many of the benefits from it, even if it's not quite as awesome as it is in other languages. In fact, one of the things you'll hear people kind of complain about a little bit with Rust is the async isn't really quite as good as it needs to be, especially when you think about the big reason for using it, which is not having to deal with those memory concerns quite as much. Anyways, if we come into our code here, to actually make use of asynchronous programming, while the async keyword and all of that is all built into Rust, you do actually have to install the Tokyo package to make use of it. So you'll see here, I have a sleep function from the Tokyo crate instead of using the sleep function from the thread module that's built in. I'll use the sleep from the Tokyo. So if you want to do like sleeping within your asynchronous coding, this is what it looks like. So one of the first things I do whenever I go to a different concurrent execution model is I ask myself, how do I put my code to sleep? And it is different in asynchronous code relative to multi-threaded code. Anyways, to make this all work correctly, we have to decorate our method where the asynchronous code starts with this Tokyo main. This is basically going to set up the asynchronous runtime. People call it an event loop. It's where it's the thing that actually manages that asynchronous behavior. Remember, I said asynchronous has a little bit more overhead involved than just doing plain threads. Here, we're going to use Tokyo to create our different asynchronous tasks that we're going to be running. You'll notice that the functions have to be defined with async, and the actual code here, in order for it to run, we have to call await. So essentially, the way that asynchronous stuff works is you create a task, which is really a future, and you take that future, you call await on it, and when you call await, that's when it actually starts executing. That gets scheduled as a task on the runtime. So here, just the act of creating this doesn't actually run it. It's the act of calling await on the handle is what actually brings it to life. So now if we come into here and we run this code. Now, most of the time when you work with asynchronous stuff, you're mostly just going to be using third-party libraries with the .await, for example, making a REST API call. You don't necessarily get into all the details of writing your code and spawning new tasks through closures and stuff, but you can do that. You're not limited to just using the awaits provided by other third-party libraries. Okay, now this is kind of a little bit different in Rust compared to other languages. I remember when I was first learning how to do asynchronous programming, one of the things that kind of confused me a little bit was the different ways that I could actually define the code for these asynchronous tasks that I wanted to create. When I first came to Rust, I was largely coming from a JavaScript, Python, C# background. And so in those languages, when I think of defining an asynchronous block of code, I think of it in terms of a function like this, or I think of it in terms of a closure like this, okay? That's typically how I think of it. And let me collapse that down so you can see the whole line. So I think of it like this and like this. So the part that I wasn't expecting when I came into Rust and started working with asynchronous code is what I call a block task. There's probably a better name for it. But you'll notice it doesn't really look like a traditional function. There's no like parameter list. There's no return value. It's just this block of code. And I remember looking at that thinking, what is that? Well, what it is that this is basically allowing us to take a block of code and put it inside of a future. And then down here, when I call the .await, it will execute this code. There's no parameters, there's no return value. It's just running this block of code. If you want parameters and return values, then you use the more traditional function syntax. So in this case here, I just have a function marked async. I've got some code inside of it that awaits. By the way, await should always accompany an async. You should not have async functions without await. The await is a kind of an important part of that. If you don't have an await, there's no need for the function to be async. Now, here with the closure, you'll notice we apply async and we apply move to the function definition. Okay, so basically we're going to have our async part of it. So there's our await, and then the move, of course, is going to take the variables declared on the outside but referenced inside the closure and move them into the closure. Anyways, to run this code, we have these different examples here. Notice on each of them, I call .await to actually run the future. In this case, the block task is already a future just by virtue of the assignment. In these cases here, the future is returned by us calling the function, but it doesn't actually run yet. But we call the function, the async returns a future, and then when you say the await, the function itself actually executes. So if I were to come into here and run this, you can see there's our code executing there. So kind of three different styles of syntax for setting up those asynchronous tasks that you want to run. The one that's probably unexpected is this one here. If you come from other languages, you're probably very familiar with creating the equivalent of a closure like an arrow function or a lambda function, or the creation of just a regular function and marking it async. Okay, let's take a look here now at doing a sequence of operations. Now, when you work with asynchronous code, kind of similar to multi-threading, I can do things in a sequence. I can gather them into a group. Keep in mind, if everything is purely sequential, you're not getting that much value out of the asynchronous code unless there's some other thing that you're able to share that thread with. But if you're just going to do one operation right after the other, and you're going through the trouble of trying to make it all async, probably not worth it. And like I said, unless there really is something else that can also make use of that thread. But nevertheless, what would it look like if I did do a bunch of tasks sequentially? So you'll see I've got 3 of those blocks here. And then down here, I'm just going to say task 1 await, task 2 await, task 3. Notice I created all 3 futures at once. So these are actual futures, but they don't actually run until I call the awaits. Okay. So for example, if I were to comment these out and then I were to run this, you see all tasks completed, but nothing up here actually ever ran. If I put the awaits back in there and run this, now you'll see task 1, task 2, task 3 are all going to do their thing. And of course, I set that to 5 seconds. I need to make that duration a little shorter. Okay, so I'm going to come on down here to gather now. Before I go over the gather, what I'd like to do is go ahead and give you the little evaluation here that I have prepared. I'm going to drop the link to it there in the chat. It's just a little jot form. It's got like 5 or 6 questions on it. Most of them are check a number or something like that. If you don't mind taking a moment or two to fill that out, either as I wrap up the demonstrations or immediately after the demonstrations, it would be really helpful. I really do read these things, and I'm using the feedback on the sessions to help make them better, but also to select new topics and things like that, and different ways of being able to work with you in a way that benefits, everybody growing in their programming knowledge, so on and so forth. All right, so let's take a look here at the gather. The idea in a gather is that these asynchronous operations are actually independent of each other. So down here, I can take these independent operations and use the Tokyo join macro, and it will basically launch all of these. And then when they all finish, will then be done. If you are familiar with, like, for example, promise.all in JavaScript or async io.gather, Tokyo join here is similar to those. This idea of launching multiple things and then waiting for them to finish. In order for this to be useful, these tasks have to be independent of each other. Okay, they can't be dependent, they have to be independent. So if we come into here and I run this code, you'll see we have our task 1, 2, 3 start. We didn't wait for them to finish, and then they end. All right, let's take a look here at the select. Same 3 futures again. Down here, we're going to basically take the first one that finishes. So you'll see here, this is similar to, let's say, promise.race or async io.wait in Python. The first one that finishes is the one that wins the race. So if we go up a folder and come into here, and we do cargo run, let's see, I think I've got it set up to be random, right? Yeah. So task 1 wins this time. Probably task 2 or 3 will win this time. There we go. We do it again. Look at that. 1, 2, 3. There we go. So anyways, these tasks, whichever one finishes first. A good use actually for something like this is when you launch an operation like call a REST API or a disk operation or something else over the network, and then you have a second one that's kind of like a timeout. So if the timeout actually finishes before the primary operation does, you could use something like this to say, oh, operation timed out, and then not use the result or ignore, cancel, whatever, that first operation. Okay. Let's take a look at our final example here. This is an apples to apples comparison of the earlier GitHub user check where it was multi-threaded, except this one is going to be using asynchronous programming. Here's the thing, though. What do you notice at the top? We're still bringing in arc and mutex. And this is the thing about asynchronous programming in Rust that's a little bit disappointing, is I still have to deal with these memory concerns even when doing the asynchronous stuff. So if we come down to here, I'm going to set up that user count the same way we did before. I'm going to increment it the same way we did before. But you'll notice I'm using Tokyo now to spawn the threads, and it's working in an asynchronous kind of way. Probably the biggest benefit, in my opinion, to asynchronous programming in Rust is when I can use things like the request crate, and I can say .await, but I don't have to get into any shared memory, and I don't have to deal with spawning things, whether it's with thread spawn or Tokyo spawn or whatever. If all I need to do is just use this HTTP client mechanism to get some data, and I can do it in a way that is going to allow me to launch multiple operations at once and get my data back and work with it. And all I have to do is say .await, throw in the async keyword and do a little Tokyo main, and that's all I have to do. Async is great. But if I have to really start getting into spawning my own closures, dealing with memory between those things, that's when the benefit of the asynchronous, in my experience and opinion, starts to really fade away. And whether I'm using a thread to spawning a thread or using Tokyo spawn, it's really the same amount of work. So you'll hear people kind of complain about that a little bit. Complain about that when working with asynchronous programming. In terms of blocking HTTP would still work in an async context, but it would be blocking. It wouldn't be asynchronous. You'd be blocking the thread while you're waiting for the response to come back. See, one of the big things in asynchronous programming is that all of your code runs on one thread. So when we did multi-threaded programming, our code ran on different threads. But in async programming, our code is going to be running on this one thread. If you put a blocking call there, then you're blocking everything on that thread. And that's the downside to it. So technically it would still work, but it would defeat the point of doing asynchronous programming. That's why when you'll see examples of doing multi-threading, people will choose the blocking version of the library, because the multi-threading is handling the non-blocking aspect of it by having multiple threads. But when people do the asynchronous version, they use a special version of the library that does the awaiting, because we're going to let the runtime manage the actual call being done by that request crate out to those REST APIs. Okay, wow, we actually got this done with under the hour-and-a-half time. And the webinar we did last week, we ended up, I think, going over by a minute or two. So I'm glad that we were able to fit all of this within the hour-and-a-half allotted time. First of all, that question about the atomic U-size zero-cost abstraction, I will post an answer to that in Discord and actually talk about zero-cost abstractions and things like that a little bit more as part of my response. If anybody wants to join the Discord group, let me give you the link to that one more time, and you can check out the answer, and maybe we can even have a little bit of a discussion about it if you're interested. If you get a chance, please fill out the evaluation. Please consider liking, subscribing to the YouTube channel, following us on LinkedIn. It's a great way to stay aware of future events. We have the next two that are currently scheduled is the one in a week and a half for the enums, structs, and traits. And then we have the leptos one at the beginning of July. I'm probably going to put in one or two more events between now and then. So just stay up to date on that, and you'll be welcome to join those. And just want to thank everybody for taking time in their day to come do this. I know each of us has a lot of things on our plate, and a lot of different people want to try to get your attention to try to talk to you about important stuff. And I'm honored that you made the effort to come out here today and do this. I hope you all have a wonderful rest of your day, and I hope you have a wonderful weekend. Thank you again for coming out.